In this video, we define the other four hyperbolic functions, and we look at their derivatives. We derive their derivatives using the quotient rule and chain rule. And then we also look at their graphs on decimals.com. So we said in the last video that the hyperbolic sine function is defined to be 1/2 of e to the x minus e to the negative x. And the hyperbolic cosine function is 1/2 e to the x plus e to the negative x. Hyperbolic tangent is defined sort of the way you would expect it to be defined, since the tangent of x is sine of x over cosine of x. Hyperbolic tangent is hyperbolic sine of x over hyperbolic cosine of x. If we want to, we can write that in terms of exponential functions this way. These 1/2s reduce and we get this function. So we can think about how this function behaves as x goes to positive or negative infinity, or derive what the graph should look like. And then the hyperbolic secant is 1 divided by the hyperbolic cosine of x. So that turns out to be 2 divided by e to the x plus e to the negative x. Hyperbolic cosecant of x is 1 divided by hyperbolic sine of x, which turns out to be 2 divided by e to the x minus e to the negative x. And then hyperbolic cotangent is sort of exactly what you would expect. It's hyperbolic cosine of x divided by hyperbolic sine of x. Or you end up with this sum of exponentials in the numerator and the difference of exponentials in the denominator. Now, we derived the derivative rules for sine and cosine in an earlier video. We said that the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine of x is hyperbolic sine of x. We're just going to derive the rules for these guys now, using the quotient rule for this one, and then the chain rule for these two. We could also use either the chain rule or the quotient rule for the hyperbolic cotangent of x. The derivative of hyperbolic tangent of x can be found using the quotient rule. Hyperbolic sine of x divided by hyperbolic cosine of x. If we call this the low function, and this the high function, and I know that this is not how it's spelled, it's just a nice abbreviation. We've got the derivative of a quotient is high, oops, I took that backwards. Low d high minus high d low over low low. And that d is a differential operator. It applies to the function in front of it. So we've got the low function, or hyperbolic cosine of x, times d high. So the derivative of hyperbolic sine is hyperbolic cosine. So I'm going to have two of those, hyperbolic cosine times hyperbolic cosine squared, minus high. And then d low, the derivative of hyperbolic cosine is hyperbolic sine. And then we divide by hyperbolic cosine squared. That numerator is actually hyperbolic cosine squared x minus hyperbolic sine squared x. And if we want to, we can write that as 1/2 e to the x plus e to the negative x quantity squared. So you're going to square the fraction and square that factor as well. And then we have the same thing here. The hyperbolic sine is 1/2 of the quantity e to the x minus e to the negative x. Square the fraction, square that. And so from here and here, you're going to have a 1/4 as a factor. You can factor that out of everything. And then here, you're going to have e to the x plus e to the negative x times itself. And here, you'll have e to the x minus e to the negative x times itself. Now first times first is e to the 2x. Outer times outer is e to the 0, so that's just a 1. Inner times inner is another e to the 0, so we've got 2 of those. And last times last is e to the negative 2x. This is just because if you take e to the x and multiply by e to the x, you're supposed to add the exponents. And if you take e to the x and e to the negative x and add the exponents, you get e to the 0, which is 1. So we've got that there. And then similarly over here, e to the x times e to the x is e to the 2x. Outer times outer is -1. Inner times inner is another -1, so we get -2. Last times last is a negative times a negative, which is a positive times e to the negative 2x. And then we distribute this negative here. And you see a lot of cancellations. These guys reduce, and you just end up with 1/4 of 4, which is 1. So this numerator is 1, and we're dividing by hyperbolic cosine of x squared, and 1 over hyperbolic cosine squared is hyperbolic secant squared. So the derivative of hyperbolic tangent is hyperbolic secant squared, and that's very similar to the fact that the derivative of tangent is secant squared. So you just sort of add that hyperbolic to it. And it turns out that they're the same. Now for the derivations of these guys, we will use the chain rule. The derivative of hyperbolic secant of x is the same as the derivative of 1 over hyperbolic cosine of x. And remember, we've got an exponent property for that. If I have 1 over x to the positive power, that's the same as x to that same power, but negative. So this is a hyperbolic cosine of x to the first power. So I can rewrite that as a hyperbolic cosine of x to the negative first power. And then we see that we've got an inside function and an outside function. Our inside function is that hyperbolic cosine function. The outside function is that power function. It's raising it to the -1. So you say, well, what's the derivative of a function to the -1? It's -1 times the original function to the -2. Put the inside function back in and multiply by the derivative of the inside. And the derivative of the inside is hyperbolic sine of x. So I'm going to write this as -1 over hyperbolic cosine of x times hyperbolic sine of x over hyperbolic cosine of x. And I know that that's probably not the first thing you would think of when looking at this. You think, okay, there's a hyperbolic cosine squared in the denominator, but I'm splitting it up like this. And remember, if we multiply straight across, we got hyperbolic sine in the numerator and a hyperbolic cosine squared in the denominator, which is exactly what I expect. But if I write it like this, it makes it much more obvious that this is a negative hyperbolic secant term, or factor, excuse me. And then this is a hyperbolic tangent term. So it turns out that the derivative of hyperbolic secant is negative hyperbolic secant of x times hyperbolic tangent of x. It's almost exactly what you would expect because the derivative of secant is secant times tangent. We just end up with an extra factor of -1, and we change the hyperbolic or the regular secant and tangent functions to hyperbolic secant and tangent functions. We can do the same thing with this hyperbolic cosecant function. Hyperbolic cosecant of x is 1 divided by the hyperbolic sine of x. Or alternatively, you can just think of that as hyperbolic sine of x raised to the -1 power. So that requires the chain rule. Here's our inside function. So we've got derivative of some function raised to the -1 power is -1 times the function raised to the -1 minus 1, which is -2. Put the inside function back in and then multiply by the derivative of the inside. The derivative of hyperbolic sine is hyperbolic cosine. And so we get, well, we have two hyperbolic sines in the denominator, so I'll write that as hyperbolic sine times hyperbolic sine. And then I've got one hyperbolic cosine in the numerator. This is negative hyperbolic cosecant of x times hyperbolic cotangent of x. And that looks very much like one of our trig rules. The derivative of cosecant of x is negative cosecant cotangent. The derivative of hyperbolic cosecant of x is negative hyperbolic cosecant of x times hyperbolic cotangent of x. Now, if we use the quotient rule here, or the chain rule here, it turns out for the derivative of hyperbolic cotangent, we get exactly what we would expect. I'm actually not going to do that derivation this time. The derivative of cotangent is negative cosecant squared. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. Of course, you're taking that hyperbolic cosecant squared of x. You have to put something into that function to get an output. So those are our functions and their derivatives. Let's explore some of them graphically on Desmos.com. So this is the hyperbolic tangent function. We didn't compute the limits on paper, but I think we can see just from looking at the graph that that function, the hyperbolic tangent function, approaches 1 and -1 as x goes to positive and negative infinity. It's relatively easy to see if we do the calculations on paper. So let's actually go back to the paper and do that. So this is our hyperbolic tangent function. It's the hyperbolic sine of x divided by hyperbolic cosine of x. And this is what those functions are in terms of the exponentials. Those 1/2s reduce, and so you just end up with that. If we look at the limit of the hyperbolic tangent as x goes to infinity, what we'll see is that as x goes to infinity, e to a very large power is a very small number. This goes to 0 and this goes to 0. If I had 1 million there, this would be e to the -1 million or 1 over e to the 1 million. E to the 1 millionth is very large, so 1 divided by that is very small. So this goes to 0 and this goes to 0, and we just end up with an exponential divided by itself. So we get 1 there. Since that limit at infinity of the function is 1, we know that y equals 1 is a horizontal asymptote of the hyperbolic tangent function. And similarly, if we look at the limit as x goes to negative infinity, the exponentials here will go to 0 because x is a very large negative number. And then if x is large and negative, if I multiply by -1, it's going to be large and positive. So this is e to a large positive power and then divided by itself. So I've got -1 of those divided by itself. So it's a -1 divided by 1, which is -1. So y equals -1 is the other horizontal asymptote. And our hyperbolic functions look like this. So we've got hyperbolic tangent here, and then we claimed that the derivative of hyperbolic tangent was hyperbolic secant squared. Desmos.com will actually calculate that for us. So if we just type f prime after typing in f, it calculated the derivative and showed that to us. But it's the same function. So either way, you can use the calculated version or the equation that we came up with and did our derivation. And I think if we zoom in a little bit, we can see that the slope of the tangent line does seem to be given by this purple function. We're talking about the slope of the tangent line to this teal function. Here's the tangent line. At 0, it looks like this tangent line has a slope of 1, and that's equal to the function value of the derivative graph. And then as x goes to negative infinity, we see that those tangent lines get increasingly horizontal. And the y values, or the slope of that line that's nearly horizontal is going to be nearly 0. And the same is true on the other side. Goes through some positive slopes there in the middle, and then it has a 0 slope again at the end. So the maximum value of that slope is here at 0. And then these are small positive slopes. So here's our slopes decreasing from 1 down to 0. And then we have a 0 slope over here. And then as we go from 0 out to here, the slopes are decreasing as well. And so it makes sense that the derivative graph would look like that. If we want to, we can check out the points on the curve and then look at their function values. The claim is that at x equals 3.2, the slope of the tangent line is 0.007. We can, that seems consistent with our picture because it has a very, very tiny positive slope. But as x gets larger, that slope gets closer to 0. And as x gets smaller and much increasingly negative, the slope goes to 0. So all the interesting things happen between approximately -3 and 3. That's where we have slopes that are non-zero. If we want, we can zoom in a little bit and we can see both of those curves. That gives us the relationship between that hyperbolic secant squared graph and the hyperbolic tangent graph. Okay, so that is our hyperbolic tangent and the related graph, the hyperbolic secant squared, its derivative. Now we can look at the others as well and just make sure that our intuition is confirmed by the graphs themselves. This is the hyperbolic cotangent graph. Remember, hyperbolic cotangent is hyperbolic cosine divided by hyperbolic sine, and hyperbolic sine is 0 at 0. So we've got a vertical asymptote at x equals 0. And now, if we look at the exponential functions that define it, and take the limits as x goes to plus or minus infinity, we find that the function approaches -1 and 1 as x goes to negative infinity and infinity respectively. So we end up with this graph that has 2 branches. The y values go from negative infinity to -1 and then 1 to infinity, and skip the y values in between -1 and 1. That's our graph. That's a hyperbolic cotangent. And using the quotient rule or alternatively the chain rule, we can derive the hyperbolic cosecant squared, negative hyperbolic cosecant squared as its derivative. But let's just think about it first before we do that. Like here's a tangent line at x naught equals 1 and plot that point. That has a negative slope right here. And if I move this back and forth, actually, let's just go from 0 to 10. Notice that all of those slopes are negative. That's a very large negative slope. It's a very steep negative slope. Or the line is very steep, so I'd expect a large negative value for the slope. And then as x goes to infinity, the tangent lines seem to flatten out. So I would expect the derivative values to approach 0. So I go from a very, very large magnitude negative slope to something that's approaching 0. But on the way there, all of this, they all had negative slopes while they were approaching 0. So that's what I would expect on that branch. And then if I go, if I look at the branch on the other side, where x is between, say, -10 and 10, and then vary x, well, it looks like I still have a bunch of negative slopes. 0 slope over here, but then at this point, we have like maybe a negative, there's a slope of negative what? I go down 1 in the y direction and then over That's 7, about -1/7 is our slope there. And then we just keep letting x get closer to 0, and they become steeper. So the slopes are all negative. They're 0 here, and then they become negative and increasingly negative. And then on the other side, they do the same thing. So that's what I'm expecting for the derivative. And the derivative turned out to be negative cosecant, hyperbolic cosecant squared. And that is consistent with our graph. We have a nearly 0 value over here and here. And then as x approaches 0, those slopes become very large in magnitude, but increasingly negative. So that hyperbolic secant squared has a limit of -infinity as x approaches 0, which is consistent with what we get when we just look at the pictures on the graph. And if you'd like to compare the y values of the graph itself and the corresponding derivative, you can do that by just choosing to label this on decimals.com. I'll post links for this in the description of the YouTube video. So that's hyperbolic cotangent and negative, its derivative negative hyperbolic cosecant squared. We've already looked at this one, we've looked at this one. And here's the hyperbolic cosecant of x. So that's 1 over hyperbolic sine of x. Hyperbolic sine of x is 0 when x equals 0. So we've got a line right there. Hyperbolic sine takes on all the values between -infinity and infinity. So 1 over that value is going to end up give us values in 2 branches. The horizontal asymptote y equals 0. The function approaches 0 on the left and right, or as x goes to -infinity and as x goes to positive infinity. The derivative hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent. And we have negative slopes everywhere here as well, if we look at the tangent lines. See, all those tangent lines are decreasing as you look at them from left to right on both branches. And so I would expect a graph that's negative all the time, and that's what we get. And it has a vertical asymptote at x equals 0 as well. If you want to, again, you could graph those points, move the tangent line around, make sure that you agree that the slope of the tangent line is equal to the value of the derivative graph. But all of that is available. It'll be available in the links under the video description. And then finally, we've got the hyperbolic secant. This is actually what's really interesting. It's 1 over the hyperbolic cosine. Now remember, hyperbolic cosine actually looks like this. So what we have is this function that is always greater than or equal to 1. So we have 1 divided by something that's always greater than or equal to 1. So it's never, so at its minimum, when we take the reciprocal, the function has a maximum at 1. And then when I divide by something very large, I get something very small. So we end up with this curve. It looks a little bit like a bell curve. And we can plot the derivative. The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent of x. We can draw tangent lines if we want to, and see that the slope of that tangent line is a negative value, and it turns out to be about negative 0.494. And then you can let those values change and see how changing x naught changes the slope of the curve. As all these slopes are negative on the right of 0, and our derivatives are all negative over there. And then the derivatives approach 0 as the slope of the tangent line approaches 0 in the original function. And then on the left of 0, all of our tangent lines have positive slopes. The functions are increasing. So as I move that tangent line around, I can see that those derivative values, whoa, zoom again. Those derivative values are positive, but they become less positive. They approach 0 as x goes to -1. So we end up with something that looks roughly like that. I think that's it. We have looked at the four other hyperbolic functions: hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. We have looked at their derivatives and the graphs of those derivatives. And so now we can summarize our new derivative rules. And remember, these are giving us formulas for the slope at particular locations. Derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. Derivative of hyperbolic tangent is hyperbolic secant squared. Now, notice that the hyperbolic sine, cosine, and tangent all have a positive 1 as a factor out front. The other three have a negative 1 as a factor. And then otherwise, aside from the SIGM sign, that positive or negative 1 that's multiplying the functions, the derivative rule is exactly what you would expect if you know your derivatives rules for your trig functions. Derivative of sine is cosine. Derivative of hyperbolic sine is hyperbolic cosine. The derivative of cosine is negative sine. The derivative of hyperbolic cosine is positive sine, hyperbolic sine. Derivative of hyperbolic tangent is hyperbolic secant squared, because the derivative of tangent is secant squared. The derivative of secant of x is secant times tangent. Derivative of hyperbolic secant of x is negative hyperbolic secant times hyperbolic tangent. The hyperbolic cosecant function is similar, and the hyperbolic cotangent function is similar. It's just all 6 of those rules that we've memorized from trig, or those trig differentiation rules, just modified a little bit. But again, remember, these aren't trig functions, they're actually exponential functions. These are how they're defined, and they have the types of graphs that we talked about. Now, we still do occasionally get, vertical asymptotes when the denominators are 0. But this hyperbolic cosine is always between 1 and infinity, so this denominator is never 0. So we don't have to worry about vertical asymptotes here or here. But in this one, hyperbolic sine is 0 at x equals 0. So we get zeros in the denominator, or which correspond to x equals 0 being a vertical asymptote. And then with the hyperbolic tangent and hyperbolic cotangent, we actually get 1 and negative 1 as our horizontal asymptotes if we take the limits of these exponential functions, or this particular combination of exponential functions as x goes to positive and negative infinity. So that's it for this video. Next time we will look at something called implicit differentiation, and that will allow us to derive the derivative formulas for our inverse trigonometric functions, as well as our logarithmic functions.